this talk has essentially, it's a talk in number theory, and I'm a number theorist, but one of the interests in the results is the applications of mathematical logic, and the audience is kind of mixed. I will try to give something to both, or maybe to disappoint both of you, I'm not sure, but we'll see. So let's start with applications to logic. That's most of you probably have heard about this or know about this. So this is Hilbert 10 problem. This was from his list of 23 problems asking the existence of a Turing machine. And back then Hilbert asked it for Z, deciding solvability of diophantine equations over Z. So that means that the input would be any polynomial f with coefficients in Z, any number of variables, and it would output yes if you can find it 0 and no otherwise. Just deciding probability. And back then, maybe historically, number theory, especially diophantine geometry, was not yet particularly developed, and Hilbert's intuition for this problem was that the answer would have been yes, and that's why probably restricted to Z, while his main interest was rational numbers, arguably, where if the answer was yes for Z, then it would have been yes for Q as well, but the other way around doesn't quite work. So let me state the main results, and then I can say more about the history, put them in historical context. So theorem 1 is a negative answer, so you can ask the same question over any reasonable ring, and so this is all joint work with Peter Koymans, and this was from 2034. So be finitely generated infinite commutative ring. Then the answer to Hilbert question is no, and I would summarize this by simply writing H10 over R is undecidable. So if you run the same question, is there a Turing machine replacing everywhere Z with R? So it takes as input an equations with coefficients in R and decides whether there is a solution in R. Then the answer is no. Finitely generated as a ring here means as a Z algebra. So it's polynomials in finitely many variables, modulus, and relations, and commutative polynomials. This is commutative. We'll hear about non-commutative rings later today, and infinite is kind of necessary, otherwise there is a simple algorithm for that. And yes, so let me tell you, let me finish the main theorems here and then tell you essentially how they reduce to a much more classical result from the 70s. So conjecture of Denef and Lipschitz, correctly, asking if you have a number field, then the conjecture that you can define Z inside the ring of integers of K in a diophantine K. Z is a subset of the ring of integers of K. Okay, then what's the ring of integers? It's diophantine. Diophantine here you can take as a definition. There are alternative definitions, but means that it's the projection. There is a polynomial in a certain number of variables, such that if you take the 0 with coefficients in OK, such that if you take the 0 set in OK, and you project it on the first variables, then that's exactly the integers. So that's what diophantine means. And theorem 2 is that this conjecture holds. Work. And it might be not surprising, at least for R equal OK, that essentially you can theorem 2 becomes a tool to reduce Hilbert 10 over OK to Hilbert 10 over Z. Because you can imagine that you start with imagine now you have your fictional algorithm over OK, then you can start with a polynomial equation over Z, and you can add for every variable one equation that is defining Z over OK that recognizes that that variable lies in Z, and there is a way to put all these in one single equation over such rings, and therefore you would have an algorithm to decide over Z. So therefore, if you can prove H10 over Z together with theorem 2 that is undecidable over Z, you would have proved theorem 1, at least when R is equal to OK. But so let me put here a remark. The full implication is harder and can be found among many other sources, but there are many other references I should mention here, but I will just mention because you find the complete proof there in Eisentrager PhD thesis implication. For instance, this includes rings of positive characteristics, which number fields are saying not much about, and that there much more is known, and you have then to glue such things, you have to do some piece of commutative algebra, that's all done in her PhD thesis from Berkeley. So, yes, so theorem 2 basically is reducing the task of proving, at least for number field theorem 1 to R equals Z, and that, of course, is a celebrated result, and I will state it in the form that I will use later in this board. So this is a combined work of Denef, building on work of Matyiasevich, Robinson, Davis, and Putnam, which is a case R equals Z of theorem 1. And I will just say it orally, but I will remind you of this in a bit. Actually, Denef proves that conjecture 1 holds when K is totally real. Sorry, I included Denef. So H10 over OK is undecidable when, sorry, that's what I put right, when K is totally real. Yeah, so the case of K equal Z was due to K equal Q, it was due to Matyiasevich, Robinson, Davis, and Putnam, and Denef generalized it to K being a totally real number field, and he proved a more precise version of conjecture 1 in that case. So the K theorem 2 was already known when K was totally real. I'm not stating it explicitly here, for reasons of space, but I will remind you of that later. And there were other known cases, like abelian number fields was due to such as Shlapentokh, and some low-degree number fields were known already. And yes, so let me mention that in this work of Denef, he introduced the idea of using elliptic curves. He didn't really pursue it in that article, but this was done later, and the results in arithmetic here that I'm going to write are all about elliptic curves, and I will build a bridge a bit later in the talk, but let me state now the main theorems about arithmetic and sort of which is the actual content of this talk. So this is theorem 3. And it's from the same work and is actually our main result. The rest was, all the other reductions were already known. And following, okay, a number field having as list tutorial places, then there exists an elliptic curve E over K such that the rank of E over K is equal to the rank of E over Ki, where I is the root of -1, and they are both positive. So I here is square root -1. It's not an element of K because K is the tutorial place. The theorem would be true also in that case, but it would be not so interesting. And yes, so there is this fun assumption of the tutorial places. Let me already mention, I will state it explicitly later, that by now, due to work of Zivina, the same theorem holds true much more generally. You can remove this assumption and you can generalize here to any quadratic extension. So this was somehow in the first implementation of the method, this assumption were very handy, and I hope I will manage to convey an idea of why and how now we have slightly better results. And here I want to take one of those, and the result is that if K is a number field, then there exists an elliptic curve E over, sorry, let me see, then for a generic elliptic curve E over K with full two torsion. One is infinitely many quadratic twists of rank exactly 1. So the cardinality of the set of twists such that the rank of E K equals 1 is infinite. Generic here would need a definition, and I will not give it formally. It's basically a very concrete property on the Weierstrass equation. If you write the equation as y squared equal x minus a1, x minus a2, x minus a3, where a1, a2, a3 are in OK, and you run a1, a2, a3 in a box, 100% of them will satisfy this assumption. So if you take your favorite, if you start throwing at random elliptic curves, then this property holds. So in particular, the corollary, which was proved, uploaded in the same day, also with a different proof by Zivina, so same people, and Zivina, is that there exists an elliptic curve of rank 1. So, okay, a number field. So generic is an empty condition, there exists E over K, such that rank of EK equals 1. And here I can say a bit more. So in this work, I mean, we didn't say it explicitly, but you can essentially, we overcame the technical difficulty of the tutorial places, and you can use this method to reprove this without the tutorial places, but that was done as anyways with slightly different method. I would say more about the difference on the methods by David, and he proved this his corollary is a corollary of a stronger result, where indeed he reproves, as I mentioned, theorem 3 in much broader generality, and he can even achieve a mixed theorem where he at the same time makes sure that this rank is 1 and it's stable. So Zivina's method can do slightly different things, and they are broadly related, but they are not exactly the same thing. And I'll say a little bit more about this. Are there any questions so far? Yes.
So in all of these, can you like compute such a curve, or is it decidable if a curve is generic in this sense?
Oh yeah, generic is a very silly condition. I'll tell you, it's a very concrete condition in terms of there are enough prime factors in all the differences in A minus B, A minus C, B minus C, and that somehow that they have congruence conditions. So it's something that you can easily check. And
but the real question is about D.
D is also algorithmic. So these proofs are in principle an algorithm to construct D. So this proofs gives you a procedure to event that provably eventually terminates giving you a D. And, not a very practical one, but yeah. More questions? Some implications. So let me say some implications. So I want to mention two, and one of them is that theorem 3 implies directly theorem 2, and I will explain later, but this is due to Sasha. So, a very nice method of Shlapentokh to, even with such a constraint on the number field, you essentially have enough flexibility to prove theorem 2. Observe, theorem 2 is a theorem about any number field. So somehow there is something going on quite tricky in that implication. And I also want to mention that theorem 4 also is an application to logic, which is due again to Shlapentokh, and I think it's work in progress, so she's filing it up, but the statement is that if K is a number field, you can define Q over K with exactly one universal quantifier put at the beginning of your sentence. So the sentence looks like it's a polynomial. You can find the polynomial over K such that the first variable is in Q if and only if for all values of the second variable there exists a choice of the remaining variables such that the polynomial vanishes. So there is one universal quantifier put, the sentence looks like this, and again it's really a formal implication. It's even, maybe even more precise, corollary 5. She formally needs just an elliptic curve of rank 1, and she can prove this as a consequence, and there is something in this implication that is somewhat related to what goes on in part of this implication, in just a part of this implication. And I will come back on that later. Are there any questions? Okay, so let me now tell you something about some past results, and what are some past results here. This before telling you about the method, and some future direction. Some open problems. So
maybe it's better to lift this one.
Yeah, actually,
because it's hard to see from here.
Oh, sorry, can go much up. Sorry. Okay, yes. Okay, so an important result which will be also helpful to explain the proof was due to Mazur-Rubin. And in some sense, it's easy to explain the proof in terms of what they did back then. So they proved basically theorem 2 conditionally on BSD. And they didn't need the full BSD, they only needed some form of parity. For instance, it would be enough to know finiteness of the to infinity part of Tate-Shafarevich groups of elliptic curves over number fields, which is slightly weaker than BSD. So let's make all these other results actually. And so some results that followed this work, one you will hear right after my talk by Ari, and this is from 2025. So let me list it here. Like this, reproof gave, so this is Alpoj, Bhargava, Ho, and Schnittman. Ari will explain this proof afterwards, and they reproved theorem 2 with an alternative argument, with a argument, and I will not say much because I will give a talk about this, but I would say that the main difference, as you will see, is that they exploit higher dimensional abelian varieties versus elliptic curves. Then there is the work of Zivina that I already mentioned, but let me mention that Zivina has on his webpage some exciting further work proving an analog of theorem of corollary 5 for ranks equal 2, 3, and 4. So he's able to go up to rank 4 and prove that every number field you can achieve these numbers as ranks of elliptic curves. So somehow there is a kind of a bit of an industry, and more recently Koymans and Adam Morgan found a way to generalize theorem 4 to hyperelliptic curve. So again, the theorem is that generic enough hyperelliptic curve, full two-torsion, the Jacobian having full rational two-torsion, has infinitely many twists. The Jacobian has infinitely many, the curve has infinitely many twists, such that the Jacobian has rank exactly equal to 1, and some future directions for this problem. I just want to mention two of them, and one is a conjecture of Mazur-Rubin, conjecture that you can reconstruct curves from their Galois, from their k-bar point as Galois said, on reconstructing a curve over a number field k from the points over the algebraic closure, not taken just as a set, but as a Galois set. So these data should be enough to reconstruct conjecturally the curve, and I believe that you can use the methods of theorem 4 to prove this for a generic pair of elliptic curves. This has not yet been done, but it's something that is work in progress. And there is another natural problem, that is diophantine stability result as per theorem 3 for general Galois extensions. This is something that is, I don't know of any applications to mathematical logic, but for number theorists is certainly interesting to prove the same type of stability results of finding elliptic curve of positive rank that do not change under a given extension. So you are given the extension again, and not just quadratic, and your job is to find the elliptic curve.
Carlo, I wouldn't say conjecture, I would say question.
It's a question, okay. Sorry.
Yeah.
Okay. Thank you. Thanks a lot. Any other?
To avoid confusion, the rank 0 should be rank 1 on there?
No, rank 1 you can't really do for general Galois extensions. There are some counterexamples of Rubin due to parity for some biquadratic extensions where
Inequality. That's greater than
the greater than 0. The diophantine stability just means that it's positive but doesn't change. But with rank 1, it's even if the original rank would be 1, there are some examples of Rubin as soon as the extension gets biquadratic, where root number things give you that the rank has to become even somehow. Okay, and then there are more natural questions like higher ranks, can you do rank 5, rank 6, and so on, that are maybe interesting mostly to number theories. If there are no further questions, let me now give you the bridge, the main bridge between the right board over the arithmetic part of the board and the logic part of the board. So this is the Poonen Shlapentokh method. And the theorem is the following. And it appears in an article of Shlapentokh, but she writes there that it was independently found also by Bjorn.
there's an H at the end.
Yeah, there is an H indeed. I was a bit confused. Okay. I was looking at my notes and I made a mistake here, but somehow I knew it was. Thank you. Essentially, the statement is the following. There is a more general statement available, but let me give you the following toy case. Let L over K be an extension of number fields. And suppose that, assume that there exists an elliptic curve over K such that the rank is exactly like in theorem 3. The rank stays the same and is positive. Then OKU, the subset of OL, is diophantine. And what goes in this proof is fairly similar to what goes in. There is one key step that appears also in this implication of corollary 5 on rank 1 elliptic curve, implying the universal the formula with one universal quantifier. So this is really crucial, and I can now explain the reduction that from theorem 3 to theorem 2. So this is due to Shlapentokh again. I think it's in a paper on the Journal of Number Theory with Mazer and Rubin. The diagram goes as follows. I will use F for the thing of theorem 2, and for the number field of theorem 2, and let me write here the rings. So here you have OF, here you have Z, and the first step is to sort of balloon this number field and place an L here, where L somehow accommodates the assumptions of theorem 3. So you add I to this, and you add just something that turns it into totally real. That will make sure that there are enough real places, sorry. there needs to be 6 of them. And I will explain this in a second. Sorry, there is a normal closure here. So L now is a Galois extension of Q, and what you do is, for any embedding of L in the complex numbers, you define K sigma to be the decomposition field for that embedding, so the inverse image of the real numbers, and you take the fixed field under that decomposition at infinity, and you have that this is a field that goes in the real number, so this is a non-trivial quadratic extension, and is exactly, L is exactly K sigma root minus 1. So we are close to be in the situation of theorem 3. And the only thing that you have to check is that K sigma is 32 real places.
Move the board up.
Oh, yeah, sorry. Is this okay? Thank you. You have to prove that K sigma is 32 real places, and that's why you put here something of degree 64. There are 6 of them. And you do a little exercise in Galois theory. There is a division by 2 going on, and you can lower bound the number of real places of this with 32. So you are in the situation of theorem 3. So now you apply theorem 3 together with Poonen Shlapentokh, and you know now that this is diophantine extension. This is a diophantine extension. But now this holds for all sigma, so you can now go down to the intersection. So you place M to be the intersection over all sigma of K sigma. And the fact that now it's kind of an exercise, if you intersect these diophantine sets, you have a diophantine set, so this is diophantine. But M now goes in the real numbers under any embedding of L in the complex numbers, and it's a Galois extension clearly by construction. This is the largest totally real sub-extension, and this is now diophantine because of the stronger version I mentioned, and they didn't write of Denef. So Denef proved that this is diophantine. This is diophantine. And now you know this is diophantine. There is now another exercise you have to do. This is transitive. This is a general property. So now this is diophantine, and now there is yet another exercise that tells you if you become diophantine over a bigger one, you were diophantine over the smaller one. So this is I got that. So that's how you somehow you constrain Z to be diophantine in OF by first sort of going up in a bigger thing, applying the elliptic curve over every quadratic extension, going down to a totally real, applying Denef, combining, getting this, and then getting this. That's it. Okay, any questions on this argument? Okay, if not, I can now tell you more about the proof of both theorem 3 and theorem 4. Because the main difference comes towards the end.
Does this trick allow you to replace Z by any OK contained in OL?
Sorry, what's the question?
Is Z special here? You're proving that given your theorem 3, Z is diophantine in OF, right?
Yeah.
Could this any pair of number fields, not just F over Q? Can you also make Q?
Oh, L over F, you mean? Yeah, I think it follows that OF will be diophantine. It follows even formally. Yeah, so. But in this proof, it's special of Z, because you really use the Hilbert over Z was already known, essentially. But once you know that, it actually follows the same, the relative statement follows. Yeah. So let me tell you how do we find the curve. So the general principle for all these proofs, and even for the Maser-Rubin argument, is to work with a family of curves. Work with family of curves, and in Aristotle it would be a family of abelian varieties, and essentially the main differences between the proofs of Zivina, the proof of Arye and collaborators, and our argument is the family. So, sort of different families will force on you different constraints on what you have to achieve, and the proof can become a little different quite different actually in the technical implementation. So, but yeah, you work with a family of elliptic curves and you want to achieve two things at the same time. As you see there, for instance, the rank has to remain the same, and then it has to be at least 0, or in the other theorem, the rank had to be exactly 1, so it means you have to be positive, but not too big. And one is to find a sample in the family where the rank is positive, and the other, at the same time, you have to control Selmer groups. I will say more for the logicians in the audience what Selmer is, and for this talk, Selmer will be 2 Selmer. In Aristotle, it will be a different Selmer group. But the main point is that ranks of elliptic curves are not something we know how to compute in general, and Selmer groups are sort of computable avatars of these objects, and they are conveniently upper bounds. I will say more precisely how in a bit, but sort of this is giving the upper bound part of the proof, and this is giving the lower bound part of the proof for either cases. And maybe it's less evident at the moment what is in that theorem, but I will say it in a bit. So in this general principle, what Maser and Rubin did, Maser-Rubin was to work with the quadratic twist family. So you start with an elliptic curve E, and you start quadratic twisting this, which simply means that you put a D in front of the equation, dy square f of x, if E naught would be with D equal 1. And so in this family, where E naught is fixed and D is varying, there is a very convenient way to write down 2 Selmer. So 2 Selmer is a fairly concrete function of D, but the hard part is the rank. So what they do in their work essentially is they prove that you can find D with small Selmer, which is giving you the upper bound part of the proof. And on the other end, here is where BSD enters in. They can make sure that a certain invariant of the curve, called the root number, is negative. And that forces the rank to be positive. So that's where BSD comes into play. From a simple computation, and this is simply, in this case, it's basically a congruence on D. It's a very explicit condition on D, but the mystery here is that there are rational points, and the depth of BSD is exactly from this simple to compute invariant. Sometimes you can infer the existence somewhere of rational points. So that's why the proof is conditional. So the main idea for all these works that I mentioned is to work instead with a family such that this condition holds generically. So work with families of curves with generic positive rank, with positive generic rank, sorry. Generic rank. And then the hard part becomes this one. So you start from the outset solving problem 1 here, that your rank is positive, but then the computable function that you get is harder to control, and harder here means that it will be a function of the complexity of the function will be given by prime values of polynomials, and the tool that replaces BSD in the proof is additive combinatorics. So additive combinatorics arranges for Selmer. So that's in a sort of a very cartoon way the way this proof works. So arranges to Selmer. So the difference between the two methods is that here you run in a full family where without BSD you wouldn't know that the rank is positive, but you have a sort of a very nice and control onto Selmer as a function of D. While instead here you make your life a bit harder, you work with families where it's not at all clear that you can control to Selmer, but you know that the rank is positive by default. And then you use tools from additive combinatorics to make sure that to Selmer is fine. So let me tell you more precisely what is our family, and there are many families now where this idea is being implemented. So the family is very simple. You start with E naught being y squared f of x, and you consider the family f of the y squared is equal to f of x. So you basically quadratic twist, so this is E naught f of d. You quadratic twist your starting elliptic curve by the values of the same Weierstrass equation. So d here will run over k except from 3 values. Just avoid the roots of f, and then this is a very nice elliptic curve. And what is not so hard to prove is that this is generic rank that is positive. So generic rank is positive, and the generic section here is, of course, x equal d, and d comma 1 is always a rational point. And you can prove that generically is non-torsion. Generic values of d is non-torsion. Generic here can be made even more precise. There is a finite list of numbers up to squares, such that f of d has to avoid that list of numbers modulo squares. So there are finitely many things modulo squares that have to happen for the values of f, and for how the proof works, you make sure that the values will take infinitely many values of modulo squares, so that is not going to be a problem. So let me write down more precisely in homogeneous form this equation, because that is very sensitive to the additive combinatorics that we use. So I write d is really an element of k, and that is crucial for the proof, not just in OK. And m and n are in OK. Okay, n is non-zero. And once you homogenize this equation, it becomes the following. Y squared is f of x, where a, b, c are the roots of f.
Could you read that? It's a little hard to see the difference between the m and the n.
Sorry, what?
Could you read the product? What did it say?
Oh, sorry. This is
hard to see the difference between the n and the m.
Maybe let me call them M2 and M1. Thank you. Oh, sorry. Good.
Okay.
Is this better?
Yeah, that's better.
Yeah. Okay. Yes, so it's now a good time to tell you whatever 2-Selmer is, which kind of function it is. So 2-Selmer is a vector space over F2 that is the kernel of a certain matrix, EDK is the kernel of 2 times that E, I will explain this notation in a second, plus omega D square matrix consisting of symbols, of Legendre symbols of the shape a character supported on a prime, evaluated in the Frobenius of another prime. So let me explain this a little bit better. So you take all the places of bed reduction of your original elliptic curve, and you take all the places above 2, and all the Archimedean places, and you take a D that is supported away from all of this, and is actually locally trivial at all these places. So then you get a matrix that has 2 times every such place. The prime divisor, omega here is the number of prime divisors of D, and this is the number of all these places, bad places that are listed. And essentially you have to know all the mutual Legendre symbols, and this is not quite the matrix, but once you know this matrix of Legendre symbols, you can cook up this matrix. So this is the type of data you need to control if you have to control 2 server. And let me tell you now what is the upper bound. The upper bound is that the rank of the elliptic curve, EDK, for us is at most the dimension of this nullity space of this matrix, D K minus 2. So when you apply it, for instance, for theorem 4, where you want to prove that the rank is exactly 1, what you're trying to get is that this matrix is almost invertible. And okay, I will explain it this time towards the end of the talk, which Selner group you have to control for the Hilbert application, but let me go back now to this by simply saying that I want to make this matrix almost invertible, and it's a matrix supported on the prime divisors of D. And D for us is a product of 4 linear forms. So you need to control the prime factorization of 4 linear forms. Okay, so the first idea now is, to apply green tau as proved in the version proved by Kai in 2023, which is a green tau for number fields, and tells you that under suitable condition on ABC, which you can fix at the beginning of the proof, you can make sure that these 4 things are simultaneously primes infinitely often, and even with a correct asymptotic form. So they're all primes. Make them all primes. Okay, so now your matrix looks like that there are 4 things here, and there are maybe 1 million things here coming from the places of bed reductions, which you don't know, and you have to make the matrix almost invertible. So there is an obvious problem here that maybe the minor of the matrix coming from the initial places of bed reduction has a massive nullity. So you maybe have a huge 0 matrix to which you are adding 4 rows and 4 columns, or 8 rows and 8 columns, and you are trying to make it almost invertible. That's not going to work. So you have to face possible massive nullity of the minor coming from bed E. Bed E 2 times bed D squared. Okay, so then the second idea is put a kappa somewhere, put an auxiliary number depending only on ABC, on the original elliptic curve, and it is here. And you can again apply Kai's theorem with a change of variable. It's basically green tau arithmetic progressions now. You can make a change of variable and make sure that this is divisible, is kappa times the prime number, and then you again might be in business if you construct your kappa in such a way that you defeat this initial massive knowledge. So you can imagine you have a massive 0 minor, and then now you make a bunch of steps that imagine a 0 matrix here, and then maybe it's a 0, 1, 1, and now it's an invertible matrix. So and this is constructed at the beginning of the proof, sort of before enforcing Q1, Q2, Q3, Q4. And now there is the serious problem in this that constrains you a lot. And the problem is that you have no control on these symbols. These Legendre symbols, you have absolutely no control. So there is no version of green tau that tells you how to do that, and up to swapping and doing some Euclidean division, this is essentially the symbol M over N. So you would need some kind of green tau that tells you also what is the square behavior of one variable with respect to the other one, and we asked also experts like Ben Green, and they, at the moment this is not something that is standard, at least. So you want to somehow avoid that, and here comes the third idea. You have a matrix here. Imagine here there is a matrix. You maybe had this very nasty initial nullity. You make kappa here to defeat that, and that's nice. And now here you have no control on the final matrix there, and the idea here is to use matrix rigidity. So matrix rigidity is simply the observation that sometimes you can arrange matrices in such a way that maybe ignoring just a few entries of the matrix, you can still make the rest of the matrix invertible, whatever happens in those final entries. Sort of a very toy example to keep in mind here is this, a triangular matrix with all 1 and 0s here. So imagine that you arrange this, and an enemy comes and starts putting star as she or he pleases, and no matter what it's done here, the matrix remains invertible. So sometimes that is possible, clearly, and that's what you do. And once you do that, that constrains you quite heavily on what you need to do on the kernel of the minor at stage kappa, and here you face a final problem, problem 3, and this is the entanglement, possible entanglement of Q1, Q2, Q3 mod kappa. So let me explain this. So you place kappa here. So observe that if I reduce Q1, Q2, Q3 modulo kappa, they are all consistently M1, because kappa divides M2, so they are all the same. So these 3 primes are not independent modulo the prime divisors of this auxiliary block that you did here, this kappa. But fortunately enough, what you need to do to achieve matrix rigidity is the opposite. You need to have control on how the prime divisors of kappa go modulo Q1, Q2, Q3. And there is a sign in quadratic reciprocity. There is an extra thing that depends on the behavior at the quadratic places and the infinite places, and that's exactly where the 32 real places are used in the proof. So maybe let me write here, final box. So, fourth idea, use the real places to disentangle. And that precisely means that you have a bunch of divisors of kappa that you want to make very independent modulo Q1, Q2, Q3, while you know that Q1, Q2, Q3 are the same modulo, they are the same thing modulo these divisors. And the idea is that when you flip the Legendre symbol, there is an extra contribution at infinity, and if you arrange things at infinity very carefully, you can essentially make them independent. And in the second version of the proof for theorem 4 for the elliptic curve, where we removed the 32 real places for theorem 4, we used to disentangle, we used places of split multiplicative reduction. We replaced the real places with some, we blamed the original elliptic curve we disentangle in that way. So that's how you can get rid of this funny assumption of the 32 real places, but the main role of that assumption in that work was exactly at this stage of the proof. And yeah, then you make your Selmer small, the rank is positive generically, and you're done. So let me just make one final technical remark to say that for theorem 3, the Selmer group that you're controlling is the Selmer group of minus f of d. You want to make sure that this is two-dimensional. Because once the Selmer group of minus f of d is two-dimensional, you know that the rank of the curve will be 0, and there is a decomposition of the rank over k of I as the sum of the rank over k and the sum of the rank of this twist. So you will make this twist of rank 0, the other twist is positive rank generically. You run this argument, and now it's both positive and doesn't change. While for theorem 4, you have to control Selmer of the curve itself, and you have to prove that it's three-dimensional. So then you use this inequality here, and you upper bound the rank that way. So that's, I think, a good place where to stop.